In this lesson, we implement a simple bypass policy for the last level cache using the RRPV predictor. Our goal is to bypass the last level cache if the RRPV predicts very early re-eviction. We will define a threshold and compute the expected reduction in cache pollution, given that stream traffic makes up 20% of all accesses. We will solve this both mathematically and graphically. First, let us understand what RRPV represents and what we mean by pollution. RRPV stands for re-reference prediction value and ranges from 0 to 3 in a 2-bit scheme. 0 means likely to be reused soon. 3 means likely to be evicted soon. Cache pollution occurs when one-time streaming blocks enter the last level cache and evict useful blocks, only to be re-evicted themselves without reuse. Here is one last level cache set, showing ways and their current RRPV values. Blocks near 3 are red and close to eviction. Blocks near 0 are green and likely to be reused. Now watch a new streaming block arrive. Without a bypass policy, it gets inserted and may knock out a useful block, adding to pollution. With a bypass policy, if the predicted RRPV at insertion is above a threshold, we skip the last level cache and send the request to memory, preventing pollution. We define the policy: bypass the last level cache if the predicted re-reference value is greater than or equal to a threshold t. We choose t equals 3, the strictest level, meaning only the most obviously non-temporal lines are bypassed. We also need a simple model of prediction quality. Assume streaming lines have 90% chance to have RRPV equal 3 and 10% equal 2, while reusable lines have 5% equal 3, 15% equal 2, 30% equal 1, and 50% equal 0. These numbers are illustrative and capture a typical separation. Let S be the fraction of stream traffic. Here S equals 0.2. Let QS of T be the probability that a stream block has predicted re-reference above or equal to threshold T. With T equals 3 from our histogram, QS equals 0.9. Baseline stream pollution rate per access is S. With bypass, the remaining stream pollution is S times 1 minus QS. Therefore, the absolute reduction in pollution per access is S times QS. Plug in the values. S equals 0.2 and QS equals 0.9. We get a reduction of 0.18. That is an 80/10,000th drop in pollution per access, which is a 90% reduction of the stream pollution itself, and an 18 percentage point reduction overall. Note, false positives reduce hits, but do not increase pollution, so they do not add to the pollution term. We focus purely on pollution reduction here. Let us visualize the effect. The baseline stream pollution rate per access is S equals 0.2. After bypass with T equals 3, it becomes S times 1 minus QS, which is 0.2 times 0.1 equals 0.02. The yellow bracket highlights the reduction of 0.18. Threshold choice trades strictness for coverage. Using our histogram, for T equals 3, QS is 0.9, and the false positive rate on reused lines is 0.05. For T equals 2, QS becomes 1.0, and false positives rise to 0.2. For T equals 1, QS is still 1.0, but false positives become 0.5. The pollution reduction depends only on QS times S, so it is 0.18 for T equals 3 and 0.20 for T equals 2 or 1. Hit rate costs, however, grow with false positives. To summarize, bypass if our PV is above or equal to threshold T. With T equals 3 and 20% stream traffic, expected pollution reduction is S times QS, which is 0.18. Graphically, we saw the bar chart drop from 0.2 to 0.02. Tighter thresholds reduce false positives at the cost of slightly less reduction. Looser thresholds reduce more pollution but can hurt hit rate. Choose T to balance these effects for your workload.